Listen carefully. Which compressor has a faulty bearing? All right. So I've just opened up a poll which asks you to identify which compressor that you've just heard has a faulty bearing, either A, B, or C. Please take a few minutes to fill out the poll and let's see what people thought.
Yeah, this is a little tricky, Sudhir. I don't know. They all kind of sounded different to me.
Yeah.
You think people will get it right?
Let's
Guess
see.
we'll see.
Okay. All right. See, like the results are coming in. It looks like most people have chosen C so far. Okay. So let's go ahead and see what the answer was. All right. So the faulty compressor was actually bearing A, right? And it looks only about 10% of you are correct on this one, right? So would you want to take your equipment offline for maintenance based on that level of accuracy? Right. This is a situation many companies are in. You might be able to identify problems more accurately than 10% in your own equipment, but in predictive maintenance, every little bit counts. My name is Sudhir Nugahali, and I'm here today with my colleague Rachel Johnson to talk about predictive maintenance with deep learning. By the end of this talk, we hope you will see how and why to explore deep learning for your predictive maintenance applications. If you have any questions, please feel free to ask them in the Q&A panel. Okay, so what are today's key takeaways for predictive maintenance? To start, small gains can yield big rewards. What I mean by that is when you operate equipment 24/7, even 1% more confidence can translate into millions of dollars in savings. So you should explore a variety of modeling approaches to achieve the best results, including deep learning. Of course, if you build or operate machines, you probably already have useful insights. To succeed with predictive maintenance, you need both domain expertise and AI knowledge. With specialized domain-specific tools and examples, MATLAB helps you do both. Finally, you'll see during this talk how MATLAB can automate the entire predictive maintenance workflow from accessing data to deploying an operation. Today, I'm going to take you on 2 journeys in predictive maintenance alongside Rachel, a mechanical engineer who wants to pursue increases in accuracy with 2 projects. In her first journey, Rachel has compressor acoustic data with labeled faults. In her second journey, Rachel has a lot of data, but not a lot of insight into what it means. So let's meet Rachel.
Hi, everyone. My name is Rachel, and I am a mechanical engineer at Membrane Manufacturing. I know a lot about the machines that we operate. Honestly, I can usually tell when something is going wrong. Of course, now our company has this new AI initiative, and they want me to start looking at our data in new ways.
But Rachel isn't an expert in deep learning or AI.
I really don't know anything about deep learning or AI. I'm a mechanical engineer, not a data scientist. So where do I even begin here?
Thankfully for Rachel, MATLAB makes it easy to get started. So in any predictive maintenance project, the first step is to consider your data. MATLAB can access data wherever it lives, whether it's in a local file system, databases, or remote cloud storage. You can also generate synthetic data if you have a model of your machine and interactively label failures. At this step, you may also want to extract useful features from your data that more clearly show anomalies or degradation. The next step is probably the most interesting part of the workflow, AI modeling. Here you will design and optimize predictive models, both traditional machine learning models as well as deep learning. As we said before, you'll probably want to try out a variety of modeling approaches and iterate on the best features for your model. Finally, all this work isn't useful unless you can deploy your algorithms into production, for example, on the edge, in the cloud, or on your desktop. But once you have your algorithms deployed, the journey doesn't stop there. You may want to use deployed results to iterate and refine other parts of the workflow, including improving your model. Okay, so let's follow Rachel on her first journey in predictive maintenance.
I've been working with these air compressors for a long time, and I can really tell just by listening when something is going wrong. But our maintenance crews have a hard time figuring out what that exact problem is, and this means more downtime and lost revenue. I think we can do better here. I've been reading a lot about predictive maintenance and how deep learning might help me interpret all of this data. And honestly, we have a lot of data. We've recorded acoustic time series data from a compressor almost continuously for the last year. I also have some written maintenance logs, so I know which data sets correspond to which of the 7 fault codes that we record. I started by using the classification learner app in MATLAB to experiment with some machine learning algorithms at first. The best I was able to do was with a bagged trees model that gave me 88% overall accuracy. That's not terrible, but I'm wondering if maybe deep learning can do better.
Okay, so let's walk through the deep learning approach Rachel took. She'll start out with accessing her audio files with a MATLAB data store, then extract audio-specific features using Audio Toolbox. Then she'll train and validate a long short-term memory deep learning network with their ultimate goal being C code generation for edge deployment.
All right, so let me walk you through the approach that I took to solving this problem. I started by first bringing the data into MATLAB using a data store, which lets me point to where all of the audio data lives on my machine. I then decided I needed to split the data into 2 parts, a training set, which I'll use for training the model, and a validation set, which I'll use to test it. I always like to start out by just exploring what the data looks like. So in this case, I can read in one of the acoustic time series signals for a particular fault. In this case, it's actually a bearing fault that we're looking at. The next step is I need to extract some relevant features to train on. I'm not really an expert in signal processing, so I decided to start just by looking at the documentation. And what I found was under signal processing, there was information on Audio Toolbox, which seemed like it might be helpful here. And look at that, there's actually a section called Machine Learning and Deep Learning for Audio. There was a whole section in here on how to extract relevant features from audio data, including a function called Audio Feature Extractor. Seems pretty useful. So this combines, extracts different combinations of audio features, and I figured I would start with that. So using this Audio Feature Extractor function, I was able to extract 10 different features using a window length of 512 and an overlap of 0. These were parameters that I could adjust. So let me just run this section, and I'll extract all the features on all of my data at once by stepping through my data store. So once I've extracted those features, I need to use them to train my model. But because I'm not an expert in deep learning, I found another example for a model layer structure, an LSTM, that was used for a similar problem. And I was able to tweak that to work for my data. So let me set up the network by running this section of code to set up the layers. And once those are defined, I can define different training options. I had to iterate on these hyperparameters during my training, but I used Experiment Manager in MATLAB to do this automatically. I'm not going to show you how to do that here, but you can look into it afterwards. So next, I actually need to train the network on this feature set. This would go a lot faster if I was using a multi-core processor or a GPU. So I'm speeding this up quite a bit, but it took about 15 minutes to train. And as we're training, on top, we can see the accuracy is increasing, and on the bottom, the loss is decreasing. And that's good. That's what I want to see. With that model I just trained, I now need to test the network using my validation data. So I'll start just by taking a look at the confusion chart. Overall, I was able to get around 95% accuracy on my validation set. So that's pretty good. So just to recap, the neural network performed better than the original machine learning model that I tried. But it does seem like the algorithm has a slightly harder time distinguishing between the bearing faults and the flywheel faults. It often gets those two confused. Let me iterate on this a bit. Maybe there's something I can do to improve these results.
All right, so what can Rachel do to improve these results? Please take a minute to answer the poll that should have appeared on your screen. You can select multiple answers from collect more data, to network hyperparameters, try a different feature set, try a different algorithm, or buy more GPUs. All right, looks like we're getting some answers coming in. It looks like most people are kind of converging on tuning network hyperparameters, trying a different feature set. Okay, that's great. Collecting more data. All right, and it seems most people have not chosen buy more GPUs. All right, so to recap, all right, so let's move on. So to recap, how could Rachel really improve these results? Right, and so I think I'm seeing a pattern here, right? So all these are good approaches to possibly improve results, except buy more GPUs, right? That would help speed up the training, but won't necessarily give you better results. So if you're interested in the details of each of these approaches, we have more details in the handout, which should have just appeared on the right-hand side of your screen.
Well, I've gone through pretty much my entire workflow now, and hey, my algorithm is working. But now I actually want to do something with it. I really don't want this to just be a prototype that sits on my PC. I want this to work on the factory floor in production so that our crews can use these results in real time. So that deployment step is really important to me.
All right, so using MATLAB, Rachel can automate the deployment process too. She can generate C code for both the feature extraction and prediction algorithms so that she can make predictions in operation from live streaming data. You can also generate low-level CUDA and HDL code if you're looking to target other hardware such as GPUs or FPGAs. If you want to learn more about deploying MATLAB-based AI algorithms, be sure to check out the Expo talk, Deploying AI to Embedded and Enterprise Systems.
Okay, so I started with my air compressors because I actually had labeled data and I knew what types of faults I wanted to predict, and that worked pretty well. Unfortunately, most of the machines in our factory aren't like that. We have industrial welding machines and we're doing scheduled maintenance on them every month because it's really important that they don't fail. But because of this, we don't see very many failures. When failures do happen, they're really unexpected and they can take down our entire, oh, excuse me, I'm getting a call. Hello? What? But didn't they just do maintenance on that machine? Oh, yeah, okay, how long are we going to be down? Yeah, this is really gonna mess up our delivery schedule. All right. Yep, I'll be right over.
Oh, well, looks like we lost Rachel there, right? So, Rachel doesn't see many failures, but when they do happen, they're unexpected and can take down the whole production line. She'd like to be able to detect when the welding machines deviate from normal operation, even if she doesn't know what the specific problem is. This is often called anomaly detection.
All right, I'm back. Sorry about that. So we have a bunch of vibration data from accelerometers on these machines, but right now, all I really know is that the data right after maintenance is probably normal, assuming our crews did everything right. So we have a lot of normal data, but it's hard to say what's going on with the data before maintenance. Honestly, most of that is probably normal too, since we have a pretty conservative maintenance schedule. We do have a few data sets that we've been able to definitely tag as abnormal, but we don't know if those are all the types of issues we might see. At least I think we can use this data to make sure that our algorithm is working properly. Most of the anomalies are mixed in with the normal data, so I started by just trying some unsupervised clustering techniques. I was able to get about 85% accuracy using k-means clustering on my validation set, but that really isn't good enough. So last week, I talked to an application engineer at MathWorks about my problem. Oh, looks like he's calling me back right now. Hey, Sudhir.
Hey, Rachel. Okay, so I thought about the application we discussed last week, and I think an autoencoder might be a good approach to try.
Okay, well, what's an autoencoder?
Good question. An autoencoder is a type of neural network that maps input data to an encoding and then attempts to reconstruct the original data by decoding. You can train an autoencoder on features from your normal data And if the network does a poor job reconstructing a new input, you can tag that as an anomaly. Let me send you over an example and you can try it out. It might work better than the clustering methods you already tried.
Okay, great. I'll try that. Thanks.
All right, I'm back. Okay, so let's walk through the approach Rachel took. After accessing her data, she extracts and ranks signal features using the Diagnostic Feature Designer app in the Predictive Maintenance Toolbox. And using the top ranked features, she trains an autoencoder on normal data and validates on the tagged abnormal data. This time, Rachel wants to integrate her algorithms into the company's new cloud infrastructure.
All right, so let me show you how I approach solving this problem. I already had my data saved, so once it's loaded into MATLAB, the first question I had was, what does this data look like before and after maintenance? I can see that the data before maintenance looks pretty different than the data after maintenance across all three channels. But instead of using the raw signals, I decided to extract some statistical features to hopefully get better separation between those two groups. To make the feature extraction easier, I used the Diagnostic Feature Designer app in the Predictive Maintenance Toolbox. So let me start just by taking a look at my raw data here in the app. I'm looking at multiple signals on the same plot here. I can actually group these into the data before and after maintenance too. Since I have a lot of data, I parallelized the feature computations across all the cores on my machine by just selecting parallel computing. So this should help it go faster. Then I need to extract some features. I'll start with just basic time domain signal features. I'm not quite sure what's going to be best at first, so I'll just select all of them. Features like mean, RMS, kurtosis. We'll compute these across all the signals and just see what that looks like. All right. So let's take a look at all of the values of my statistical features for each of the signals in my whole data set collected in a table. Now, I could have also extracted features in the frequency domain. This would require me to calculate the power spectrum for each of the signals in my data set too. I ended up not needing to do that though, because the basic statistical features actually worked pretty well in the end here. But I'm more interested in which features are most important. So I ranked my features using a t-test. Here I can see which features are the best candidates for model training. So I decided to just pick the top 5, but I could have decided to use all of them. So once I'm done extracting these features, what can I do with them? Well, I can actually generate a MATLAB function to automate everything that I just did in the app. And that was pretty easy. So now that I have all of my features in MATLAB, I'll split the data again into a training set and a validation set, and then I'll prepare my data for training. So Deere sent me that nice example of an LSTM-based autoencoder, which I was able to reuse and train on my data with just a few tweaks. So I'll train the network now. Once I've trained the autoencoder, let's see how the model performs on the validation set. So if we take a look at this plot, what you'll see is on the left, the error is really high, which means the model doesn't reconstruct these signals very well. On the right, the error is low. So it's clear that the model performs better on the data right after maintenance. This makes sense since I trained the model on all the normal data right after maintenance. But what level of error actually means there's an anomaly here? So I took it one step further and tried to automate the detection of anomalies. To do this, I'll define an anomaly as a point with a reconstruction error greater than some value times the mean. So I'll play with this threshold, and it looks like a threshold of 4 gave me a 70% accuracy. As I change this threshold, the autoencoder categorizes more signals as anomalies. And it turned out that a threshold of 0.5 gave me a validation accuracy of over 99%. I'd say that's pretty good. So those results looked pretty good. It's clear from the data that the reconstruction error on the abnormal data is higher based on the error threshold I selected. And I was able to get 99% accuracy on my validation set. We'll have to see how well that works on new data coming in from the field.
All right, so we mentioned earlier that Rachel wants to deploy her algorithm in a cloud production environment. If you want to learn more about deploying MATLAB-based AI algorithms into production, be sure to check out the Expo talk, DevOps for Software and Systems, Putting Algorithms and Models in Operation. All right, so it's been 6 months. Let's see how Rachel's doing.
Hey everyone, good to see you again. So ever since those initial predictive maintenance efforts, our projects have really taken off. We've increased our uptime by 10% and by being able to better plan our maintenance schedules and avoid surprise failures. We've even started to look into how to expand our analytics to an entire fleet of machines at multiple locations. Ideally, we want to have hundreds of machines streaming live data to the cloud. And in the future, we're thinking about using Predictive Maintenance Toolbox to predict remaining useful life based on historical data. Oh, and by the way, I got promoted.
All right, so Rachel's story is based on specific predictive maintenance projects by companies around the world, like Airbus, who detected defects in aircraft pipes using deep learning, or RWE Renewables, who created a virtual temperature sensor to detect anomalies in wind turbine bearings. And recently, a group at LG Energy Solution in Korea developed a condition monitoring system using deep learning in MATLAB, which was ultimately deployed as an interactive application. To learn more about any of these engagements, please check out the handouts. Okay, so to recap, we walked through 2 stories that show the development of deep learning-based models for fault isolation and anomaly detection. When small increases in accuracies can have a big impact, you should try different approaches. Deep learning might be the best approach, but other methods may also work better. In this case, Rachel was able to leverage domain-specific tools, which help develop deep learning models that ultimately increase uptime at membrane manufacturing. She was also able to automate the entire workflow in MATLAB, including the deployment to both embedded hardware and the cloud. Thanks, everyone.